Yes, I can see it. So I quickly give an introduction for Enrico. So Enrico Ravera, he did his bachelor, master's, and PhD in the University of Florence with Claudio Lucinat and Ivano Bettini. Then also did a postdoc at CERM, or the institute there, in the same group. And then since 2017, he's an assistant professor in Florence, and his research interests lie in the fields of paramagnetic NMR, of EPR, and also in integrative structural biology. And it's the last thing basically where he will talk about today. Enrico, the stage is yours.
Thanks for the introduction, and I also want to thank Sarah for giving a brilliant introduction of DEAR so that I don't need to say anything about that, basically. This is a photo of the place I come from. The numbers are the proton Larmor frequencies of the NMR magnets, and you see that we only have a single EPR spectrometer, so this is one of the reasons why we are not very often around at the EPR conferences. Okay, I directly jump into the maths. I hope it doesn't get boring too soon. This is not a slide probably for this audience. This is what the DEAR curve looks like from the mathematics standpoint. This is just to say that the equation can be recast. First, you define structure factors, which make life easier for to handle that. But then you have to move from continuous description to discrete description using a number of external points, and therefore you then can go on and solve the least squares problem in the matrix formulation, which is the thing that Sarah brilliantly showed before. The problem with this is that the matrix of the structure factors is short and large, which means that there are too few experimental points to compete with the number of points that we actually want to fit. So this is an ill-posed inverse problem, which admits an infinite number of solutions, which are all equivalently good. And on these grounds, one must introduce some kind of other information. This is usually done with the Tikhonov regularization, where you impose an additional matrix that takes into account the unwanted features of the distribution that that you're going to reconstruct, which could be, for instance, the things that are commonly used are the slope and the curvature. The matrix form of those is this, nothing really nice to see. The important thing that I wanted to make clear is that since the problem admits an infinite number of solutions, you must impose information from outside. And the information that you feed from the outside must in some way represent the thing that you know. So you may have some criteria, Dimitris Vergun calls them perceptual criteria, that make your distribution look wrong if they are not fulfilled, like too many peaks or discontinuities, or the slope being too large. Or the other way to cope with the problem is to apply a prior model, which Sarah has shown. So you say, my distribution is a Gaussian, or two Gaussians, or three Gaussians, or four Gaussians, and you do your fit on these grounds. In any case, you have to choose the information that you're feeding to your problem. For a change, I will discuss a little bit of experimental data, which also relate to NMR. So we add a little bit more of experimental information. besides providing information from the DIR. And these are pseudo-contact shifts and residual dipolar couplings. The pseudo-contact shifts are basically the shift that you get when you have a paramagnetic center which has a magnetic anisotropy. So the protons which are sitting on the lobe of higher susceptibility experience a shift which is usually downfield with respect to what you would have in the diamagnetic complex. If you are on the side where the susceptibility is smaller, you get a negative shift. And the distance dependence is very nice. You have the magnetic susceptibility, which is indicated by circles, the axial and the rhombic components, and then you have an angular dependence on the position of the nucleus with respect to the frame provided by the magnetic susceptibility itself. When you have a large magnetic anisotropy, you also get a very nice additional feature, which are the residual dipolar couplings, because your molecule gets oriented, and the orientation reintroduces the anisotropic interaction. This is assuming that the magnetic field is quite strong, which is the case for NMR. As you see, the alignment depends on the square of the applied magnetic field. The good thing is that they depend on the same magnetic anisotropy tensor as the pseudo-contact shifts, and they also have the peculiar angular dependence, which defines the orientation of each NH vector with respect to the metal. This is a particularly appealing from the analytical standpoint, say, because this ensures that for every alignment system that you have, say you have 3 different metal ions with 3 different magnetic susceptibilities, you get exactly 5 independent eigenvalues in this, or singular values in the singular value decomposition. So if you have 3 metals, you get 15 independent measures. And this is very nice for providing representations. It's less nice because, of course, it means than PCS, because PCS have a lot more of information, because they are also encoded by the distance from the metal of each NH pair, which means more information. If this, so back to the point, we are basically looking for reconstruction of average observables in systems which experience a large degree of mobility. And as we said before, the problem is heavily underdetermined. So let's go back to the RDC example. Say that you have 15 independent singular values in your matrix. Implies that you can basically reconstruct the data, all your experimental data, with 16 conformations. No less, no more. Which means that if your system can experience more than 16 conformations, and this is obvious that your system can likely explore more than 16 conformations, you may find different combinations which explain the data. If you do the same calculation with DIR, it roughly ends up with around 3 singular values per decay, which is, by the way, one of the reasons why CERM's data could be fit with 3 Gaussians, and the 4th Gaussian provides overfitting. So what does this really mean? So what does underdetermination really mean? Take a look at those numbers here. So this is a distribution which gives an average position displacement on X of 54.26 and our average displacement on y, which is 49.83, and the standard deviation is 16.76 and 26.93 in the two directions. Okay, all the following images will have the same statistics. Which means they can reproduce the experimental data in the same way, including the datasaurus. And therefore, there is in a way, there is a risk of introducing a personal bias. So the biologist may like the dinosaur more, and the astrophysicist may like the star more. And so, how do we get about this problem? And here, back, I kick in a little bit more equations because I like them. So your average observation is the integral over all the available conformations weighted by their probability, p of x. Then you know that the averaging reduces the variability of the observables. So the mi are spread over a significant range, the average m are significantly reduced. This is an example using a disease. And if all the states are equally allowable, then you get the exact average value, which is 0. However, as I said before, the Karateodoris theorem tells you that observables which are averaged over any probability distribution on the surface of your space, which in this case is an ellipse, 2 dimensions ellipse, can be obtained averaging a finite number of points. In particular, if you are in 2 dimensions, the simplex is of dimension 3. So you need 3 points to fit your data. If you are in 3 dimensions, you need 4. If you are in 4 dimensions, you need 5. So it's the number of dimensions plus 1, the number of points that you need to invoke. So for our disease, we said 5 per each metal, so it's 6. For PCS, it's roughly 60 for a protein of 140 amino acids, 61. For deer, 3 independent datasets, 4 points, and so on. For small angular X-ray scattering is 2, so you need 3 confirmations to fit your data. And one of the reasons why this, I particularly believe in this research, is that there are dozens, literally dozens of different approaches, which have been published over the years, and each of those provide the additional information, as we said before, in a different way. And basically, they're all mathematically, they're all legitimate. There's no assumption whatsoever that you can make to make one ensemble better than the other. Now, the thing that made me really curious is that in the end, if you take to the extreme the reasoning which is behind the construction of the different approaches, they can basically divide it into 2 categories. Those responding to the maximum entropy principle, and those responding to the minimal entropy or maximum parsimony principle. And retrospectively, if you look at the literature in the, like 20 years ago, the ensemble averaging approaches were mostly maximum parsimony, because the computational power was not enough for helping in big ensembles. And now, as the molecular simulations are getting better and better, they are getting longer and longer. So they are sampling the sampling of the experimental of the conformational space is becoming extremely extensive, and the quality of the force fields is improving dramatically. then the maximum entropy reconstructions are becoming more favored. Well, these are a few examples which are quite popular. The ensemble optimization methods by the Blackledge group. You kick in different ensembles, you calculate dozens of those, and then add them up. And since the sum of the solutions is still a solution, you basically get a more complete description of your system. Well, maximum entropy, that is the most, nowadays is becoming the most popular in general, is how does it look? Well, it looks like all the accessible states are given a weight which is as close as possible from 1 over the number of conformations that you are sampling. So if you need to impose a large weight on a conformation, it means that the entropy of your system is not big enough, or not particularly big. On the other extreme, you have the maximum parsimony approaches. And the maximum parsimony approaches are really, there are literally hordes of them. In all the cases, the situation is very simple. You take a few conformations, which is, in the best case scenario, one more than the dimensionality allowed for by your data. And you test how much your data can tolerate a given one conformation. And then you take the next, and then you take the next. So if you do it in a sample and select way, you will likely sample those points which are with those conformations which better represent the data. If you do it in a sample and in the EOM approach, as I said before, you will see that the data which are selected more often are those which are closer to the experimental data point. And the reconstruction that you get is extremely different in theory. So the maximum entropy solution is basically as flat as it can be, whereas the maximum parsimony solution is as peaked as it can be. And they only converge in the case of the experimental data being close to one of the extremes. Let me directly skip to one conclusion slide. The thing is that as far as your variability is very large, the methods will actually explore all the different ensembles of conformations that you can get. And the difference can be extreme. And the maximum entropy will favor a distribution all over the place in the prior distribution, and the maximum parsimony will select basically randomly conformations around the ensembles around the conformational space. But when you get closer and closer and closer, when your experimental data points gets closer and closer and closer to the boundary, which means that only a subset of the conformational space is sampled, then both the maximum entropy approach and the maximum parsimony approach will find high weight on the conformations which are close in the data space to your experimental point. And this is, I believe, particularly important because assume that you think that your system is extremely flexible. You expect your reconstruction to be scattered all over the place. And then you take one calculation using maximum entropy and one calculation using maximum parsimony. And what you get is that the conformation with the larger weight in maximum entropy are the same that are selected more often in a maximum parsimony approach. Then this is an hint for your system to be less mobile than what you were thinking in the beginning. So basically the suggestion that I would like to make is do not, if you want to approach an ensemble averaging problem, do not rely on a single method, but use a couple of those. the two extremes. And this is the practical example. What you get with DIR is that if you have a distribution that is here, the one on the left, which is obtained by using NMR data and small angle X-ray scattering, you kick in the information from DIR and you get a market selection. And in particular, the DIR data suggests that our PET system, calmodulin, tends to stay with the C-terminal domain lying towards the observer in this picture, but this is basically biological conclusion that I how to say, not particularly relevant. Maybe the important message is trust different methods, because mathematics is suggesting you a lot more than what you expect from a single method. This project dates back to several years ago. It was my master's project back in 2009. So a lot of people went by and are now contributing to the project. This is the list of the contributors to the last things that I've shown. And thank you for your attention, and I'm happy to take questions.
Okay, thank you, Enrico, for this talk. And again, if you have questions, you can raise your hand. Gunnar already said, I unmute you. Gunnar?
Okay, so isn't this problem to a large extent solved if you have a large number of distance distributions? Because then you do have the information on the width of the ensemble. So then the maximum parsimony approach will, or the result of the maximum parsimony approach will get much closer to the result of the maximum entropy approach.
This is a very nice way to see the thing. I was telling it from the other side, but basically you're right. The real issue is that if you know that your system is not particularly constrained, like if you think about calmodulin, it's four amino acid residues which can rotate freely, and if you sample all the Ramachandran space, you easily end up with say, if you sample extensively enough, you have around a billion of accessible conformations, and you will never get a billion of experimental distance measurements. However, what you're saying is exactly correct, because as the more data you add, the more information you add, independent information you add, the more conformations you need to use. And you will reach the point where the number of conformations that you need to use is basically the whole pool that you have sampled by molecular dynamics in the extreme limit. And then the maximum parsimony and the maximum entropy will give the same result. Exactly.
Thanks.
Okay. Other questions or comments from the audience? So maybe I have just one more. So is there any, so is it really just a variability where you can make a physical argument for one of the two, or is it really just a completely mathematical argument, basically?
Okay, I like this question, thanks. The answer is, how much do one really knows about the system under investigation? So this is a very philosophical question. It's not real science. It's just philosophy, maybe. And the thing is, let's say that you know everything about your system because you created like a molecular ruler, those that Gunnar used for the calibration of DIR analysis. you know really everything about those systems. And so the information that you add to your reconstruction has a very profound meaning because it has the chemical meaning. On the other opposite, when you have something that you really don't know anything about, you have to ask yourself several questions. So first, is the prior extensive enough? And the answer may be no. But assume that the answer is yes, which is, again, not to be taken for granted. Then you have to ask yourself, do I trust that my system is heavily mobile, or does it move a little? And then when you take if you take the combination of the two extremes, you really see that if your system is not very mobile, even if it may look mobile, you get a very good match between the prediction of maximum entropy and the prediction of maximum parsimony. And this is the kind of information that you're looking for.
Okay.
Okay, and then you say, okay, my assumption is correct.
Okay. Okay. More questions? I don't see any. If that's the case, I would like to thank you again, Enrico, and also Sarah again for these nice talks. I hope you kind of enjoyed the format that we decided to kind of dilute this a bit, that it's every month. So the next regular meeting will again be on the last Friday of August. It might include a tutorial, but we're still planning. And there will also be Asia Pacific editions, and please check the website for the timing, because sometimes they're nice for Europe, sometimes they're nice for America. So please check them, and you will also get the Zoom links there, because the Zoom link of the Asia Pacific editions will be different because I can't host it 4 in the night, or I don't want to. Yeah, thanks again, both the speakers. Thank you, and have a nice Friday or a nice weekend, depending on where you are.
Bye.
Bye-bye.